you can think of like air flowing over an airplane wing or water moving through a pipe we often use in fluid dynamics. And we consider the real world effects of viscosity. There are some limitations when we get near solid surfaces though. So what's the issue with potential flow when we get close to a solid boundary? Well, potential flow is great because it simplifies things by assuming that fluids have no viscosity. But in reality, all fluids have some degree of viscosity and the stickiness causes friction, especially near solid surfaces. If you think about honey flowing off of a spoon, it doesn't just slip off instantly. It kind of sticks and then flows slowly, and that's due to its viscosity. But it doesn't really reflect how fluids actually behave near objects. That's where this concept of boundary layer comes in. It's this thin layer of fluid that forms right next to the solid surface. Viscosity dominates the flow behavior. These boundary layers almost look like thin film that's clinging to the object. Fundamental concepts is the no-slip condition, which basically says that the fluid right at the surface is actually stuck to the surface. At the surface, it has zero velocity. It might seem counterintuitive, but that's what exactly happens. And this no-slip condition creates what we call a velocity gradient within the boundary layer. Speed gradually increases as you move away from the surface until it reaches the speed of the fluid further out, which we call the free stream velocity. So if I imagine like a leaf floating in a stream, the water right next to the leaf surface would be perfectly still, like holding a flat sheet of paper upright in the wind. The air flowing over that paper creates a drag force that's trying to push the paper over. This boundary layer affects everything from the drag on objects to how fluids mix and transfer heat. So, turbulence is fascinating. It's essentially a transition from the smooth, predictable laminar flow. We see swirling eddies, random fluctuations in velocity and pressure, and increased mixing. While turbulence does enhance mixing and heat transfer, it also creates a lot of energy dissipation, which ultimately leads to higher drag. The eddies create friction and resistance as they interact with the surface. So what causes the shift from laminar to turbulent flow? It's a complex process, but it's primarily driven by factors like the speed of the flow, the roughness of the surface, and even tiny disturbances in the surrounding flow. So if you think about like a river, a really calm, slow-moving stream is probably going to have a smooth laminar flow. But as the water speeds up or encounters rocks and obstacles, you start to see those chaotic swirling eddies.
That no matter how smooth the surface of an object is, the air will always stick to it, meaning that the velocity on the surface is always zero. At the other extreme, we have what is called the free stream velocity, which is the velocity of the undisturbed air far away. As the undisturbed air meets the leading edge of the plate, it will stick to it because of the no-slip condition. And as the air travels across the plate, this layer of air sticking to it will grow thicker and thicker. Now this region, in which the air moves slower than the undisturbed free airstream, is called the boundary layer, and within this region the viscous forces are dominant. Outside of the boundary layer, the viscous forces are much less important and sometimes even ignored in fluid modeling. You can have a laminar boundary layer in which the layers of air move nicely parallel to each other and to the surface, or a turbulent boundary layer which is filled with vortices featuring velocity variations in all directions. If the undisturbed air itself is laminar and there's nothing to trip the flow, the boundary layer will start off as a laminar one. Now, as the air moves across the plate, the distance traveled since the leading edge increases. And if we use this distance traveled from the leading edge as the characteristic length for our Reynolds number calculation, it's clear that the Reynolds number will keep increasing as we travel across the plate. When the Reynolds number crosses a critical value, which can be different for any application or geometry, the laminar boundary layer will transition into a turbulent one. Now, a turbulent boundary layer features a completely different velocity profile, which can have a dramatic impact on the separation location and the friction and pressure forces on your object. In applications like airplanes, where the shapes are smooth and streamlined, it's important to keep a laminar boundary layer as long as possible, because a turbulent boundary layer will increase the friction drag, and it is typically also thicker than a laminar boundary layer, which increases the effective thickness of the airfoil, which increases the pressure drag. In less streamlined applications, it can be beneficial to trip the boundary layer into a turbulent one. Turbulent boundary layers carry much more momentum and typically push the separation location further downstream. That's the reason why golf balls have dimples, or why athletes wear special suits or even shin tape to reduce the weight they leave behind and thus reduce aerodynamic.
For turbulence, we use the concept of Reynolds number. Reynolds number is a dimensionless quantity that compares the inertial forces in a fluid. It helps to predict the fluid flow patterns in different situations by measuring the ratio between inertial and viscous forces. Higher Reynolds number indicates turbulent flow. Flow becomes turbulent, the boundary layer still exists, but it undergoes some pretty dramatic changes. Compared to a laminar boundary layer, a turbulent boundary layer is thicker. It has much steeper velocity gradient and it experiences much higher rates of momentum and energy transfer. So, for example, you can take mixing of chemicals in a reactor. In these situations, the increased mixing and energy transfer is caused by turbulence. Mixing and momentum transfer within a turbulent boundary layer gives it more energy to overcome those adverse pressure gradients that can cause the flow to separate. So in a way, turbulence can actually help delay or prevent flow separation. So like with the dimples on a golf ball, they create turbulence to make the ball fly further. The dimples strip the flow into turbulence earlier, reducing drag and allowing the ball to travel a greater distance. Let us consider a flat plate suspended in a uniform stream of velocity v infinity and temperature T infinity as shown in the figure. The length of the plate in the direction of flow is L and its width is W. The local values of the friction factor, Nusselt number and the Sherwood number can be seen in the table for the laminar flow. Look at the important dimensional numbers that are considered. Prandtl number. Prandtl number is a dimensionless quantity that relates viscosity of a fluid to thermal conductivity, indicating ratio between momentum transport and thermal transport capacity of the fluid. High Prandtl number indicates high momentum transfer, and thus heat transfer plays an important role in design.